All right, good morning. Just picking up with what we have had with operations between functions. And again, we've looked at so far sums, differences, products, as well as quotient functions. And now, just for what we have from page 225, and we have three specified functions, okay, and we have in the form of f of x, g of x, and h of x. And for what we have in the case of f of x, okay, so we have f of x is equal to negative 2x, and we have g of x, okay, we have this as the absolute value of x plus 4. And for what we have in the case of h of x, okay, we have equal to 1 over x minus 3. Okay. And looking at what we have for functional values, okay, at specified inputs, okay, so we got in this one, okay, so for number 10, okay, we're looking at g minus h whenever x is equal to 2, okay. And so now you can use either the specific case or the general case, and I'll just show you just a couple of approaches here. Okay, now if I were to take, let's say, just going back to g minus h of x, okay, and if I put this in expanded form, okay, so this would be g of x minus h of x, and then filling in, okay, so we have for g of x, okay, we're going to have the absolute value of x plus 4 and we have minus h of x, so we have 1 over x minus 3. Okay, so we have the formula sort of laid out, and in the case of where x is going to be at 2, so we have for g minus h of 2, okay, so I have g of 2 minus h of 2, and filling in 2 for x, so we have the absolute value of 2 plus 4 minus 1 over 2 minus 3. And I'll just work on down here. Okay, so you have the absolute value of 6. And we have minus 1 over negative 1. And we have the absolute value of 6 is 6. And we have minus negative 1. And again, subtraction of a negative is going to translate to, in this case, addition of the positive. And so we have for the outcome here, okay, this winds up at 7. And again, just another approach here. Okay, if I were to take just right away, okay, so we have with g minus h of 2, if I just take the specific cases right away, and what I mean by this, okay, so we have with our functions g of x and h of x. Again, g of x is the absolute value of x plus 4. So again, you have g of 2. Okay, we have equal to the absolute value of 2 plus 4. Again, we have the absolute value of 6. So g of 2 is equal to 6. As for what we have in the case of h of 2, okay, so again, h of x we have at 1 over x minus 3. And so with x at 2, so you have 1 over 2 minus 3. And we have 1 over negative 1, so this will come out to minus 1. And so just going back to what we have for g minus h of 2. Okay, so again we have g of 2. So that is going to be at 6. And we've got minus, okay, and h of 2 we have at negative 1. And just for the follow through, okay, so you have 6 minus negative 1 becomes plus 1, and 6 plus 1 is equal to 7. So this is just another way that you can get to the final result in this case. Now, and if you're looking at just one input to deal with, I kind of like this approach. But if I had to deal with several inputs, like I had to find like g minus h, not only a 2, but let's say 0, negative 22, 57, 44, 100, whatever inputs. If I had to do several inputs, I'd say it might be a quicker route if you started out with the general case, as was the first application for this problem. All right, now for what we have in the case of number 12, okay, and still working around this particular trio of functions. I'll go ahead and copy this. Let's see. There we go. All right, so we have for number 12, okay, so we have for this problem, okay, so we have h times g of 4. Okay, now I'll show you just the general case and the already specific case for this problem. And now, if I were to take h times g of x, so we will have h of x times g of x. Here we have 1 over x minus 3. And we have times, okay, the absolute value of x plus 4 and so we would have for each value of x, okay, h times g of x will be the absolute value of x plus 4, and then we have all over x minus 3. Okay, now for h times g of 4, so again we have h of 4 times g of 4, and just taking what we have with x set to 4. Okay, so we have the absolute value of x plus 4, so we have the absolute value of 4 plus 4 all over, then we have x minus 3, so we have 4 minus 3. So we have the absolute value of 8 over 1. Absolute value of 8, okay, is 8 over 1. So we have for this output, okay, we arrive at the value of 8. Right. And just going, let's say, so this is using the general case for the onset. But again, if I go with the specific case right off the bat, so we have for h times g of 4, again we have h of 4 times g of 4, so we have with h of 4, okay, so I have 1 over 4 minus 3. And that's going to go to 1. And as for what we have for g of 4, we have the absolute value of 4 plus 4, again, which we have to be the absolute value of 8, which goes to 8. All right, so for h times g of 4 with this approach, okay, so you have h of 4, which we have at 1. We have times g of 4. G of 4 we have at 8. And we have 1 times 8 is equal to 8. So a little different pathway, but still arriving at the same result. And now, and we'll just be looking at the specific cases for the rest of this set of problems concerning that trio that we have among the functions f of x, g of x, and h of x. And now, and we have in the case of number 14, we now have for this problem, okay, we're looking at f plus h of 5. So this is going to translate out, okay, once we expand, okay, so we have f of 5 plus h of 5, and we can go ahead and just arrive at the specific values. Okay, so we have with f of 5, f of 5 we have equal to negative 2 times 5, and negative 2 times 5 becomes negative 10. And for h of 5, we have 1 over 5 minus 3. And that is equal to 1/2. So we have in the sum between f of 5 and h of 5. So at f of 5 we have at negative 10. And we have plus, and with h of 5, again, h of 5 is going to be at 1/2. For what we will have here will be a non-integer total. So we have negative 10 or negative 20 halves plus 1/2, and this will end up at minus 19 halves. And again, you could have used the general case, but I decided to go with the specific case since we're looking at just one input to work with. Now, for what we have in the case of number 16, okay, this time we have h over f of 7. So here we have h is 7. All over f of 7. And just taking what we have here. So we have with h of 7, again, h of x is equal to 1 over x minus 3. And with x at 7, we have 1 over 7 minus 3, which is going to be 1/4. As for f of 7, okay, we have f of x equal to negative 2x, so f of 7 is equal to negative 2 times 7. So we will have at negative 14. And just placing the inputs. Okay, so h of 7, again, we have at 1/4. And that is situated all over f of 7, which we have at minus 14. Okay, so we have a ratio between a fraction and an integer. And to get out of this complex fraction notation, complex is where you have at least a fraction in the numerator and or denominator, not the letter I. Okay, so we have, so for 1/4 divided by negative 14, okay, if I divide by a number, it'll be the same as multiplying by its reciprocal. So we can say we have 1/4 times negative 1/14. And here we have a positive times a negative, which will be a negative. 1 times 1 is 1. and 4 times 14 is going to make 56. So for h over f of 7, okay, the result here we have at minus 156. All right. Now, in the case of what we have for number 18, okay, so still working with the same trio of functions. Okay, we have another ratio where we have h over g of -4. Okay, so we're going to have h of -4 all over g of -4. And just specifying the inputs. Okay, so we're involving h of x and g of x with the input at -4. So we have for h of -4. In this instance, we have 1 over -4 minus 3. So you have 1 over -7, and by then you can just go ahead and write this as -1/7. As for g of -4, we have the absolute value of -4 plus 4, and the absolute value of 0 is equal to 0. And so we have, upon filling in, so for h of -4, okay, we're going to have it minus 1/7. Then we have all over g of -4, which is going to be at 0. And guess what? We have in this ratio, the bottom value is 0. So for 18, h over g of -4 turns out to be undefined. And again, the reason for this is that you cannot divide by 0. Okay. All right. So this is what we have for the trio of functions that we have for f of x, g of x, and h of x. Now, for what we have for the subsequent problems, and this time we have involving the functions r of x, p of x, and q of x. And for what we have in this trio, so you have r of x is equal to -3x. And we have that p of x is equal to x squared plus 3x. And for what we have in the case of q of x, okay, q of x we have equal to the square root of 1 minus x. Okay, and now we're going to be looking at resulting operations between functions as well as their domain. And now for just looking at the individual items, now r of x equal to -3x. Now this expression we have in x is given in direct terms. There's no fraction, and there is no even root radical. Okay, so for r of x, okay, there are no restrictions. And p of x, okay, we have x squared plus 3x. Both of the variable terms are given in direct fashion. So we also have no restrictions. Okay. Now for what we have in the case of q of x, we have equal to the square root of 1 minus x. And again, because we have an even root radical, and since the real number system does not allow for the even roots of a negative, okay, so 1 minus x cannot be negative. Okay, now 1 minus x, as long as q of x is given in direct terms, 1 minus x can be 0 as well as positive. So 1 minus x can be greater than or equal to 0. And in terms of expressing what we have along the lines of x, so taking 1 away from both sides, so we have that negative x is greater than or equal to negative 1, and then we have expressing in terms of positive x. So if I multiply or divide everything in the inequality by negative 1, or again multiply or divide by negative, again the dynamic that will play out is that the direction of the inequality is going to change. So we have for x, we have this to be less than or equal to 1. So we have for the restriction placed upon q of x, we're going to have that x must be less than or equal to 1 in order for this function to be defined in the system of real numbers. So just looking at the initial setup. Okay. For number 20, okay, we're looking at p minus r of x. And for what we have in the case of p minus r of x, okay, if you notice, okay, we have the functions p of x and r of x involved, okay, and we can go ahead and tackle the domain, okay, because again, the sum, the difference, and the product functions will all have the same domain, and their domain will be defined by combining the restrictions, if any, of the immediate functions involved. Here we are involving p of x as well as r of x, and guess what? Between p of x and r of x, okay, there are no restrictions at all. So we can go ahead and arrive at the domain. And if there are no restrictions at all, now the domain is going to be the set of all real numbers. Okay. Now for what we have in terms of how the output is going to appear, again we have p minus r of x. That is equal to p of x minus r of x. And so for p of x, we have x squared plus 3x. And minus r of x. Okay, so you have minus negative 3x. And tell you what, I'm just going to move down. Okay, so we have upon removing parentheses, and the reason I labeled using parentheses, okay, so this is for p of x, and again we have subtraction and then followed by r of x. So here we have x squared plus 3x, and subtracting negative 3x, we have the addition of 3x. And so for p minus r of x, okay, this will come out to x squared plus 6x. Okay. Again, this is going to be the result. And since there were no restrictions between p of x and r of x, the no restrictions again would roll over to the sum difference, which we have here, as well as the product functions. And so we have, once again, the domain to be the set of all real numbers. All right. Now, in the case of what we have for for number 22, okay, we're still involving, okay, the same functions. And now we're looking at r times q of x. Okay, so for r times q of x, okay, what's going to happen here is that we're involving the functions r of x and q of x. Okay, and again, sum, difference, and product functions will all have the same domain, and their domain is going to be formed by combining the restrictions of the functions involved. Now, r of x itself, for the r part, has no restrictions. But in the case of q of x, okay, to be able to work with q of x, x has to be less than or equal to 1. So we're kind of looking at the q part here. And so for this problem, okay, the restriction is going to be that x is less than or equal to 1. And just looking at what we have on a visual basis. Okay, so we have at 1, okay, so we have equal to 1, so 1 is included. Everything else is going to be less than 1. So you have a ray that's going to go continuously to the left, out in the direction of negative infinity. So for what we have in the case of the domain, of r times q of x, and it's going from the graph and translating into interval notation. So this is your inequality solution. This will be your graphing solution that defines the domain. And for the domain, so you have a parenthesis, opening, okay, so you have going from negative infinity up to and approaching 1 and including 1, okay, and so 1 is going to be in the bracket. Okay, so you got the domain, and in terms of what we have for the function itself, okay, so we have with r times q of x, so you have r of x times q of x. Again, r of x we have at negative 3x, and q of x we have as the square root of 1 minus x. And that will be the end result right there. And again, the restriction, just looking at it, would come from the square root of 1 minus x, and we already had that laid out for with q of x, the restriction not only for q, but also rolling over to the sum, difference, and product functions between r of x and q of x, where we have this particular domain as the result. Now, for what we have in the case of number 24, if you hold on for a second, yeah, I'll get to that part. Okay, so we have in the case, let's say for 24, okay, now we're looking at q over r of x. Okay, now remember, the sum, difference, and product functions will all have the same domain. Okay, but, and it'll be on the basis of, combining the restrictions of whatever is involved. Now, if it, okay, so the burden with the domains of the sum, difference, and product functions, you have just combining the restrictions. Now, in the case of taking a fraction, a quotient function, the quotient function could have still a different domain, okay, and just for what we have here, and I'll give a case where one of these is already going to be a fraction. We'll get to that in a moment. But for Q over R of X, okay, now you have R of X has no restrictions. Q of X has it where X is less than or equal to 1. Now, through the framework of, just combining the restrictions between R of X and Q of X, there's nothing from R of X, and there's nothing from P of X, but we're not working with P of X. But for Q of X, we have that X is less than or equal to 1. So I'm going to say that in the case of the restriction, and I'll put emphasis on this, you have the restriction so far is that X is less than or equal to 1, and this stems from Q of X. But now, because I'm dealing with a quotient function, there might be a restriction that results from taking the simplifying of the ratio that does not appear among any of the restrictions already specified. So we have with Q over R of X. Okay, so you have Q of X over R of X. And Q of X, okay, we have the square root of 1 minus X. And R of X, we have at negative 3X. Okay, and guess what? This ratio is already in simplest form. Now, in the case of the restrictions, again, I said the restriction so far came from Q of X. Okay, so again, from the square root of 1 minus X, which you have for Q of X, again, X must be less than or equal to 1. However, we have R of X. Now, R of X has no restrictions, but since R of X is situated in the quotient function in the denominator position, it's going to follow that negative 3X cannot be 0. And from this, X cannot be equal to 0. And this time we have with the restrictions. For the restrictions that we have placed upon Q over R of X, again we have that X is less than or equal to 1, but also we have that X cannot be equal to 0. And so for what we have here, we have X is less than or equal to 1, but you also have the added restriction that X cannot be equal to 0. Okay, so we have the numbers involved. Okay, we have 0 and 1. Okay, now we have in terms of the individual exclusion, we have the X cannot be equal to 0. So you can just like graph a hole on 0. Now for X is less than or equal to 1. Okay, now 1 is going to be included. Now for less than or equal to, now 1 is included. Now we're going to have an array that is going to go to the left. Now, had it not been for the fact that r of x was in the denominator, okay, I would have the array to go continuously, but for what I have instead, okay, it's going to have a bit of a blip that's going to occur. Okay, so you have starting from 1, so I have activity going to the left, and had it not been for the added restriction, x is less than or equal to 1 will be a non-stop ray going out to the left. But since 0 is excluded, okay, I have to bypass 0 as I continue to go out to the left. Okay, so just resuming activity with the ray going to the left. This time we have the lower limit, okay, tending to negative infinity. All right, now for the domain of this function. Okay, so for the domain of the function, okay, so we have, again, reading in order from left to right. Okay, so I have going from negative infinity, approaching but not including 0. So I have a parenthesis, and then we have going past 0, approaching and including 1, and the 1 is going to be in the bracket. And we'll say that, okay, now for number 26. Okay, so going back to the very same trio of functions, and it looks like we're going to be flipping what we had in 24. So for 26, okay, and this time we have r over q of x. Okay, and for r over q of x, okay, so you have r of x over q of x. Okay, and to let me mention this. I'm going to bring this on down here. Again, we have a quotient function. Okay, and just combining the restrictions at this stage. Okay, now, again, we have a quotient function, so the determination of the domain is not just simply combining the restrictions of the functions involved. Okay, but again, we say we have the restrictions so far. Now the dynamics can still change, but for the restriction so far, this comes from q of x, where x is less than or equal to 1. Okay, now for r of x over q of x, working with the function. Now r of x, we have negative 3x. So negative 3x is now at the top as opposed to being on the bottom. And q of x, we have the square root of 1 minus x. Now, for the function itself, okay, so you have negative 3x all over the square root of 1 minus x. And now, in terms of the restrictions, now, again, now q of x is already prescribed as being the square root of 1 minus x. So again, x was less than or equal to 1. However, there is another restriction, and that is 1 minus x cannot be equal to 0. Okay, and so just looking at what we have here. Okay, so Okay, 1 minus x cannot be equal to 0. And so x cannot be equal to 1. Okay, and this is where a little bit of graphing can be a benefit. Okay, so you have the centerpiece value at 1. Okay, x cannot be equal to 1. Now we have x is less than or equal to 1. Okay, and
I didn't get that. Did you?
okay, so you have, sorry about that. So you have x is less than or equal to 1. Okay, so you have the x cannot be equal to 1. So looking at combining the restrictions. Okay, so we can no longer have the equal to 1 part. This is going to mean, in effect, that x is less than 1. Okay, so we have a hole on 1. This means we're going to have a ray that's going to go continuously out to the left. Okay, so we have, in the case of the domain, okay, of r over q of x, okay, so you have going from negative infinity, approaching, but not including 1. Okay, and just to kind of give you a little composite summary, okay, say if we have and we'll say we have something like, say we have given f of x is equal to 1 over x plus 3. And g of x, okay, we have equal to, let's say, the square root of x minus 4. Okay, and say we have determining the domain, okay, so we have for f plus g of x, f minus g of x, and f times g of x. Okay. All right. Now all of these will have the same domain, okay, and they'll be formed by combining the restrictions for f of x and g of x. Okay, so for f of x, okay, to be able to work with f of x, x plus 3 cannot be 0. And so in this case, let me change this. I want to give you a visual. Let's say I have 1 over x minus 7. Okay, so you have x cannot be equal to 7. Now as for g of x, we have for the restriction on this one. Again, x minus 4 cannot be negative. So if you think of x minus 4 as greater than or equal to 0, in case you have the x is greater than or equal to 4. So for the sum, the difference, and the product functions, again, we're going to have the same restrictions. And this is going to be combined with x is greater than or equal to 4. And just looking at what we have for the domains throughout. Okay, so we have with the values of concern. Okay, so you're looking at 4 and 7. Okay. And again, we have the x cannot be equal to 7. Now for the square root of x minus 4. Okay, so you're looking at x is greater than or equal to 4. Okay, so we're going to initiate with the line segment. Okay, starting from 4 going out to the right. And had it not been for the exclusion of 7, okay, I would have had a ray going continuously to the right. So once we get past the hole at 7, okay, so you have a ray going continuously to the right from here on out. Okay, and so again we have going throughout to infinity. And it's going to turn out, okay, that for the domain of the sum, difference, and product functions, for the domain, okay, so we have starting from and including 4, approaching but not including 7, and then for the rest of the values, have going past 7 and going all the way out to infinity. So that's going to be the domain for these 3 operations. And again, if I had f of x over g of x, again, just looking at what we have on the basis side, the restriction so far. Okay, so you have x cannot be equal to 7, and x is greater than or equal to 4. These are the restrictions so far, just combining the restrictions for f of x and g of x. But again, looking at how things are going to play out, we can still have a different domain with the quotient function. Okay, so you have f of x over g of x, and f of x we have 1 over x minus 7, and g of x we have with the square root of x minus 4. And again, if I divide by a denominator, it'll be the same as multiplying by the reciprocal of that denominator. So for what we will have in effect, you're looking at 1 over x minus 7 times the square root of x minus 4. And so for what we're going to have in effect, okay, so to be able to work with f of x, again, f of x, we have 1 over x minus 7, so x could not be 7. to be able to work with g of x, okay, so far, okay, x had to be greater than or equal to 4. But for what we have now, if you notice, okay, g of x, okay, you had x cannot be equal to 7, x had to be greater than or equal to 4, but guess what? Square root of x minus 4 is in the denominator. X minus 4 cannot be 0. So in this case, we have that x cannot be equal to 4. So it's going to turn out that with the restriction, we had initially that x was greater than or equal to 4, but since x cannot be equal to 4 because of x minus 4 being in the denominator, we're going to have our restrictions will now be that x cannot be 7 and that x has to be greater than 4. So we have with the numbers 4 and 7. Okay. 7 again is excluded. And since x is greater than 4, where I had a bracket or a solid point on 4, I'm going to have a hole instead. Okay, so you have, again, a ray going continuously out to the right. And so it's going to follow that for the domain of this particular quotient function, okay, so for the domain of f over g of x, okay, this time 4 is not included, so we're going to have a parenthesis around 4. And we have approaching but not including 7, so I have another parenthesis. And this will be in union with those values of x greater than 7. Okay. And so for the sum difference and product functions for what we have regarding f of x and g of x, okay, these will be the same, where 4 is included in the notation. Whereas with the quotient function, it's almost the exact same thing except 4 is not included. Okay. Everything else being the same. All right. So these are samples of what we have with the sum difference products and quotient functions. Now there is another layer of working with functions, and this will be in the case of what we have in working with compositions of functions. And for what we have regarding the composition of functions, now upon first glance, it's going to look like the operation of multiplication. And the reason for that, you will have, like, what separates the variables is going to be a circle, and we might mistakenly read that as like a dot indicating multiplication between functions. But now for functions, f of x and g of x, okay, you're going to have a composition, one symbolic display. Some might call this fog x. But you have like an open, like a circle separating the f from the g. And just reading verbatim, okay, you would have this as f composed with g of x. And for what we would have operationally, okay, so we have for f composed with g of x, okay, so you're looking at f of g of x. And we have for the reverse order, okay, so like some might call it goth x. And this is going to be read g composed with f of x. So we have for g composed with f of x. Okay, so you're going to have this to be g of f of x. Okay, so you'll be looking at interchanging, okay, what will be the, you have like an input-output relation. And whatever's inside the parentheses, okay, that is going to be the input. Whatever is outside, okay, that is going to be the output. And just reversing the sequence of the functions in the compositions. Okay, so again, whatever ends up inside the parentheses, once you compress the composition notation, okay, again, what's in parentheses is going to be the input. That which is outside is going to reference the output. And let's say that just a sample of looking at compositions between functions for defined functions in f of x and g of x. And let's say if we were to look at compositions and we'll say we have given, let's say I have a couple of linear functions. Okay, we'll say we have f of x is equal to x plus 2. And we'll say that we have g of x, okay, is equal to 2x plus 3. Okay, now for what we're going to have, at least for the first composition, for f composed with g of x so we're going to have f of g of x and you could replace the g of x with 2x plus 3 in the parentheses. But another way that you could look at this is that we have with, okay, so you have f of g of x. Again, f is going to be the output, and with g of x is going to be the input. So if I'm operating in accordance with f, what do I do with the input? Now just keep in mind in reference, you have f of x equal to x plus 2. Okay, f of the input is equal to the input plus 2. Well, over here, we have f of the input, and the input we have at g of x. So f of the input is equal to the input plus 2. So we have f of g of x is equal to g of x plus 2. And guess what? Specifying what g of x is. Okay, so g of x, okay, we have 2x plus 3 plus 2 and we have for this result, okay, we have 2x plus 5. Now for the other composition, and we have for g composed with f of x. So we have with g of f of x. Now I'm going to operate in accordance with what I have assigned for the function g. Okay, so we have in the pattern, okay, so g, the input, equals 2 times the input plus 3. Now for what I have over here, okay, you have the input is at f of x, so I'm looking at 2 times f of x plus 3, and specifying what f of x is. Again, f of x was given as x plus 2 okay, and distributing. Okay, so you have 2x plus 4 followed by the addition of 3, and so we have in the outcome, okay, we have at 2x plus 7. Okay, now we have the same functions to work with, and if you notice, we had different compositions. Okay, so if you have again, if you reverse the sequence of the functions, even though you're working with the same functions, you might have different outcomes in the compositions just due to how the functions are sequenced. Now let's say if you have another case here, say we have f of x, now say it's equal to x squared minus 3. And we have that g of x is equal to 2x plus 1. So we have with f composed with g of x. Okay, so we have f of g of x. Okay, so this is our functional notation. And again, in terms of what to do with g of x, again, we have the dependent function f. And again, we have f of the input is equal to the square of the input minus 3 with the input at g of x. So you're looking at, in effect, you have g of x squared minus 3. And what is g of x specifically? Well, we got 2x plus 1. And for what we have in the follow through, okay, so for the square of 2x plus 1, okay, we've got 2x plus 1 times itself. And if you think of the FOIL method, first product is going to be at 4x squared. Outside and inside products, we have each at 2x and combining. Okay, so we have 4x. And we have 1 times itself is 1. And then we take away 3. And the result for f composed with g of x will be 4x squared plus 4x minus 2. and reversing the order of the functions. For g composed with f of x, so I have g of f of x. Okay, so with g as the exterior and f of x as the input. So operating in line with g. Okay, so g, the input, is equal to 2 times the input plus 1. And with the input at f of x, so I have 2 times f of x plus 1. And now f of x we have as x squared minus 3. And we have with the distribution, okay, so we have 2x squared minus 6, okay, followed by the addition of 1. And here this will come out to 2x squared minus 5. Okay, now, just like as was the case with the functions individually and also with the operations, okay, there is going to be an element, okay, that we have regarding domain. And I'll try to reduce the amount of terminology involved. Now for the domain of the composition of functions, okay, it's going to involve 2 factors here. Okay, so the domain, the composition of functions. Will be formed by combining the restrictions of the input function and also of the output function, which will be the composition itself. So yeah, the composition, again, I'll just put emphasis on this, the final output. And just a little couple of samples here. If we're looking at, let's say, we're just looking for the composition where we have f composed with g of x and its domain. And say we have given, okay, we'll say we have for the first item, we'll say that f of x is equal to 2x. And g of x is equal to x plus 7. Okay, and so for f composed with g of x, okay, so we're looking at f of g of x. And again, we have f of x. Okay, f of x, f is going to be the output function, so you're looking at f of the input is equal to 2 times the input. And we have on the same route here, okay, so you're looking at 2 times g of x. And 2 times g of x, this is going to be 2 times the quantity of x plus 7. So we have for this composition, okay, this will land at 2x plus 14. And it's going to mention, okay, so we have, with the input function, okay, so you have g of x equal to x plus 7. And because you don't have a fraction or an even root radical, okay, there is no restriction. And guess what? For the output, for x plus 14, the output, again, we have at 2x plus 14. And because we don't have a fraction or even root radical, also no restriction. And where the twain shall meet, okay, since there's no restriction between the input and output, okay, we have no restriction at all. So this means this is going to signal that for the domain of this composition, this is going to end up being the set of all real numbers. Okay, and just second and final case here. Okay, now we have, just say if you have a radical. So you have f of x equal to the square root of x minus 2. And g of x is equal to 2x minus 14. Again, still working with f composed with g of x. Okay, so you have f of g of x. And again, so you have f of x equal to the square root of x minus 2. So again, f of the input is equal to the square root of the input minus 2. And replacing g of x with 2x minus 14. It's going to follow that for the overall composition where we have f composed with g of x. Okay, you have 2x minus 14 followed by the subtraction of 2. And so this will be 2x minus 16. And so so this is the resulting composition. And in the case, again, just kind of going back to input. Okay, so you have 2x minus 14. Again, this has no restrictions. However, in the case of the output itself, for the output, because you have a square root, 2x minus 16 cannot be negative. Now it can be 0 or positive. So 2x minus 16 is greater than or equal to 0. And we have 2x is greater than or equal to 16. And we have a division by 2. Okay, we have the x is greater than or equal to 8. And so we have, in this one, okay, we have the only restriction comes from the output, since there's no restriction on the input. Okay, so the only restriction is going to be that x is greater than or equal to 8 for this whole composition. And so for the domain, of f composed of g of x, think of it like a number line, solid point on 8, ray going to the right, and in integral notation, so we have closed at 8, and we have going all the way out to infinity. And so that would be the domain of that particular composition.